Okay, so today's lecture is about Euler and Euler's famous identity. This is the only one in the whole identity sheet that we haven't spoken about. So today's the day. It's a huge, huge day. This is perhaps one of the most brilliant, beautiful, and admired identities in the entire universe. Okay, and of course it was brought to you by my buddy, the all-time champion, Euler. He calculated like others breathe. The most interesting man in the world. So just putting this equation up here sort of should tell you that there are so many things to explain here. If you're sort of new to this stuff, let me just run down some of the things that are probably the right things to explain. First question that comes up is, what in the world is E? Where did that come from? Of course, E was made famous by Euler, the constant E, and of course I and theta. And what does that mean? And why is this true? And for what? What is it good for? So, and how? How do you actually use it? So there are so many questions that come up that I think it's best if we break this lecture down into two servings. This is almost like having too much cake at once, huh, Diego? Is that right? So this is too much for one lecture, so we're going to break it down. We've got a helper here, and Jimena's going to show us today. What we're going to do is just explain how. How do we actually use this identity? And maybe we'll talk about E just a little tiny bit. And then we will actually leave some of these major questions for tomorrow. That meaning these ones: why and what's it good for? I'll tell you just a little tiny bit of what it's good for now, but we won't actually get to using it till maybe another day because it's too much. You're looking at like 5 pounds of chocolate Belgian cake here. It's too much for one day. Okay? Okay, so let's take the first one. What is E? E is a constant number. It's approximately equal to about 2.71828, which is exactly my website. You guys might have seen it, www.271828.com. This is the website I use for my classes. It's my favorite number, first of all, and it's one of the greatest numbers of all times. No, it is the greatest number of all times. It's the envy of all other numbers. But that doesn't really tell you the whole story. It's sort of related to pi, but it's kind of like as famous as pi, but perhaps more refined. You know, pi is like a Volkswagen. This is like a Bentley. But that still doesn't tell you the whole story, and unfortunately, the whole story may be out of context here. So you probably should watch the videos on the algebra class or pre-calc class. One of those should have a more thorough explanation of what E is. So you guys have to pay more money for that. My mother always said, when you're good at something, you don't do it for free. Not really. I got that from the Batman movie. Alright, so I can't tell you the whole story. I can only tell you for now that it's approximately 2.781828. It's the envy of all numbers, and it has some amazing properties. Alright, that's all we get today. So then the next question is, what is the deal with this equation? What's the big deal? The genius in Euler was this following idea. Before Euler, people looked at exponents in the following way. If you take any old number, for example 5, and you'd use some exponent like 2, it was clear exactly what people mean by 5 to the second power. It would mean 5 written 2 times, so it's 5 times 5. That was not a big deal. 5 to the 4th power, that would mean 5 times 5 times 5 times 5. 5 multiplied by itself 4 times. Okay, that's what people used to do before Euler. And people even got kind of fancy and they started even doing things like fractions. What does 5 to the 1/2 mean? Well, it means half of a 5, which would just mean just like this part and this part, just half of a 5. No, I'm kidding. It would mean this half, the geometric half, which means the square root of 5. Okay, and that was well understood. So people could handle integer or natural numbers as exponents. Natural number, no problem. Even fractions, no problem. Even you could even do this, 3.5. That would mean 5 times 5 times 5 times half of a 5, geometrically speaking. That was not a big deal. That was well understood. Even negative numbers, -3, that would mean 1 over 5 to the 3rd. People could handle that. But no one, ever had the guts, the audacity, or the creativity to do the following. Try 5 to the I. Ooh, yeah. Ooh, oh no. I know, huh? No one ever had the idea to try to stick in there not a negative number, not a positive number, not a fraction, but something outside of the real number line. And no one had the guts to do that until Euler came around. And not only did he do it, but he did it with great elegance and grace. It was probably divine inspiration. I don't know where he got it from, but not only did he do it with I, but he did it with not only did he do it with 5, but he did it with E. And he said I to any angle theta is equal to cosine theta plus I times sine of the theta. Now this changed the world completely. And it's crazy where he got it from. It's hard to understand sometimes where this stuff comes from. It's like, where did the Mona Lisa come from? Before Da Vinci drew it, there was no Mona Lisa. So all this stuff, where does it come from? It comes from divine inspiration. It's people that have probably are signed up to Twitter with God, maybe. I have no idea how they come up with this stuff, but they did. And so he said, e to the I theta is equal to cosine theta plus I times sine theta. And so you could play that game for any real angle theta. So that means e to the I, 45 degrees is equal to cosine of 45 degrees plus I sine of 45 degrees. Radians, no problems. E to the I pi, that would be equal to cosine pi plus I sine pi. Incidentally, we'll come back to this one later. E to anything, e to the I 2 pi would be equal to cosine 2 pi plus I sine 2 pi. You guys getting it? Well, I'll show you how to do 5 later, but e to anything, e to the I, well, that looks like e to the I to the 1 times 1. So this would be cosine 1 plus I sine of 1. And when there's no units there, of course, the default units are radians. Whoa. The default units are radians. So anything. So I think the best way to put things in perspective is to take a really, really, really big picture point of view on this thing. Let's suppose you went away to a far away galaxy and you look back at the Earth and you try to look at the Euler identity and try to make meaning of it. What does it really mean? What is it good for? Here is the big picture associated with Euler's identity. You can imagine 3 worlds, alright? 3 worlds. One world is here, one world is here, and one world is here. In this world you have monomials. Okay, in this world you have binomials, and in this world you have Euler world. Now, let me put things in perspective here. In the binomial world, you have things that are binomials. So, for example, you have things like 3 plus x, or you may have things like I plus 4, or you may have things like square root of 3 plus 2. If these binomials happen to be complex numbers written in standard form, then something really, really, really special happens. Okay? And Euler sets up this bridge between the 2 worlds. It says, hey, I got a bridge here. I will unite these 2 worlds where numbers don't look like that. They look like this. They look like e to the I times 30 degrees. They're monomials. Not only monomials, but they're monomials written in exponential form. And to set up this bridge here, Euler says, I know exactly how to take you from these things, the complex numbers written in standard form, to exactly this world, the world where everything's written nice. Now, I'll say more about that later. But the great power in it is the fact that this world is not very computational friendly. You can think about this world as the world of Mondays, the world of Prozac, the world of synthetic artificial cheese. That's this world. You can think of Euler's world as utopia. Everything is so nice. You can add, you can multiply, you can do everything. And the great bridge that unites these two worlds is this equation that if you have cosine theta plus I times sine theta, you can rewrite that as e to the I theta. This is the uniter. This is the bridge that sets up, that unites the two worlds. Now, more than that, you have even some monomials. They may look like monomials and they don't look that good. For example, you could have 7 or 1 or the square root of I or the square root of or the cubic root of I, and say, what? What is that, the square root of I? The number that when you square you get I? Not that easy to figure out. However, Euler also sets up this world, says, hey, any complex number that you've got here, I can set up a bridge, a really nice, happy bridge into my world. And in this world, oh, things are so easy. Square roots are so easy. Powers are so easy. This is the great utopia of worlds. And so, if you took a big picture point of view, this is exactly what the Eulers Identity does. This, as crazy as it seems, it just seems like such a plain equation. It really is a uniter of worlds. It unites three different worlds. The world of binomials, specifically the world of complex numbers written in standard form. And it sets up a bridge where it says, hey, every one of these numbers, you can write it as an Euler number. Okay, that's one of the bridges. And the other one is, even if they're already monomials, I can still write them as Euler bridge. Any single complex number in the world, whether it's a binomial or a monomial, I can rewrite in Euler form. And in this world, there is no Prozac, there is no artificial cheese, there is no Mondays. Everything is so easy here. Adding, multiplying, dividing. This is the greatest world of them all. Okay? Well, I'll take it back. I don't know about adding, but certainly multiplying, dividing, and taking exponents and square roots. This is where you want to be. Okay?
Papi.
Yes, Jimena? You excited too?
Papi.
Yes.
Can we go somewhere now?
Can we go somewhere now? Right in the middle of Euler. What are you thinking, Jimena? So what's going to happen here is eventually computations here, problems, questions, intuitions in this world will become computations, problems, intuitions in this world. The same for this. Like I said, this is way too much for one lecture, so we're going to leave that for tomorrow. Today, what we want to do is a real modest goal here. We just simply want to practice crossing this bridge. That's all we want to do. We simply want to practice crossing this bridge and applying the Euler identity to cross that bridge and to see how every single number can, in fact, every single complex number can, in fact, be written as an Euler number. Even if they're monomials or binomials, doesn't matter. As long as it's a complex number, you can always cross this bridge and write it in Euler form. That's the only thing we want to do today, for the rest of today. Just practice crossing this bridge. What we want to do next time is really start exploring the power of crossing that bridge. What can you do once you know how to cross it?
Papi?
Yes?
Water.
So let's practice crossing that bridge. The good thing is that you already know how to do it. You remember when we converted polar coordinates to Cartesian and vice versa? This is exactly the same identity, the same way. Suppose you've got some complex number on this is the complex plane. You could have a complex number, say like thank you, 3 plus 2i. Three plus 2i. This would be 1, 2, 3, and 1, 2. 3 over, 2 up. That's 3 plus 2i. And when we did polar coordinates, we said, hey, you could look at this as a polar coordinate, and hold on just a second. So back when we were doing polar coordinates, if you could find this length of the distance from the point to the origin, we call it r. If it's positive, we call it r. We actually also have possibility to be negative, and that happens here too. But we won't let that worry us for now. And we call this theta. Then the amazing thing is that we already know exactly how to do this. It turns out, according to Euler, this will be exactly r e I theta, where this is the r and that's the theta. And since you already know how to do that from before, when we were turning this, when we were converting from Cartesian to polar, remember we had to find the r and the theta. This is exactly the same r and the same theta, but it turns out that this is exactly how you convert to Euler form as well. So in this case, let us find the r. To find the r, we know that the x squared plus the y squared is equal to r squared, and we know that the x is 3 and the y is 2, so 3 squared plus y squared, no, 3 squared plus 2 squared is equal to r squared, so that would be 9 plus 4 is equal to r squared, so 13 is equal to r. So my r could be plus or minus. Remember, just like before, there are infinite many ways that you can convert because there are infinite many names for this point in polar coordinates. Same thing happens here. There are infinite many ways to cross this bridge and to represent it using Euler form. Your theta could be this, or it could be that plus 360, or it could be this theta with a negative r. All those things still apply. In this case, we're going to go with a positive square root, even though the negative one would work as well. So we've got r is equal to the square root of 13. Theta, on the other hand, we could go with theta is equal to tangent of 2 over 3, tangent inverse, which is approximately, there are many thetas that work again. Infinite many thetas could work. Let's see if this one works. What you do is you shift, first of all, clear everything, shift, tangent 2 over 3, and that gives you 58. That's in radians, so I'm going to change that to degrees. So we shift, and then we do it again, tan inverse of 2 over 3, and that's equal to 33.7. About 33 again, there are infinite many thetas that work, but 33.7 would also work. 33.7 degrees. So 3 plus 2i is the same thing as square root of 13 times e to the I times 33.7 degrees, approximately. See how nice that is? And if you don't believe me, it's easy to check to see if you did it right. Here's how you could check. You could change colors to the checking color, blue, and you just go like this: square root of 13 times that, which was equal to cosine of 33.7 degrees, plus I times sine of 33.7 degrees, and then this would be square root of 13 times, well, cosine of this angle would be, what would it be, 3 over adjacent, this is the square root of 13, this would be adjacent over the square root of 13, plus I times, sine would be the opposite, which would be 2 over the square root of 13. Then you distribute the square root of 13, that would give you 3 plus I times the square root of 2. So that's the key right there. The r and the theta from polar coordinates are exactly the r and the theta that you need to convert from standard form of a complex number to the Euler form. That is the bridge that takes you from this form to that form. All you do is plot them on the complex plane and use the r and the theta, the same ones that we used before for polar coordinates, and that takes you to the bridge right there. Isn't that amazing? That's the bridge right there. And it even works for monomials. Think about it. I'll give you some more examples. Suppose you have a dotted white line for an axis, and take this point, that one right there. say it's 5. Can you tell me what is the r and what is the theta here? The r is equal to 5 and the theta is equal to, again, there could be infinite many thetas, 0 or 360, etc., etc. But definitely 0 degrees and 5 works. So this is the same thing as 5 times e to the I times 0 degrees. Perfect. That would be one way to convert. Or it could also be 5ei times 360 degrees. That would be another way to convert. Or it would be negative 5 ei times 180 degrees. That would be another way to convert, where you first face the 180 degrees direction and then you walk backwards 5. These are all the same point. That one and that one and that one. And that's a way to convert. For example, 5, you can convert it into Euler form. It's 5 times e to the I times 0 degrees. Or 360, or a bunch of other ones. I won't list them all, but this is certainly one way to convert it. Okay, even I. Let's see, how about this one? Now this one. Make all this disappear. What about this point right here? I. How would you convert that? Well, again, you first have to figure out the r. As long as you can figure out your r and your theta, you can figure it. You can get the conversion. Okay. The theta is pretty easy because this is 0 degrees. That's 90 degrees. So theta is 90 degrees, and the r is 1. So this is the same thing as ei times 90 degrees. There's another part of the bridge here. I is the same thing as, there are many ways to convert, but this is one of them. I 90 degrees. Amazingly enough, the bridge brought to you by the man who calculates like others breathe. Okay, there's more. There's more to that. Watch this. Suppose you wanted to let me see. Suppose let's erase this. How about we do some timeless stuff? Timeless. I mean timeless. What if you wanted to convert, say, this one? This point over here. -1. Whoa, -1 on the complex plane. How would you convert it? Well, it's easy. All you do is first figure out the r, this length, and also figure out the theta. This is 0 degrees, this is 90 degrees. How much is that? 180 degrees. Right? Or pi. Either way. Or there's many ways to do it. Or -180 degrees would also work. Or 360 plus 180 would also work. I tell you, there are infinite many ways to do it. But certainly, theta equals pi will work. And r is equal to 1. So here's another crazy way to look at it. -1 is equal to... -1 is equal to e. The r is 1, so I won't even write it. R is 1. I times pi. Whoa, 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 whoa. And now you have something amazing here, something timeless. Here, just to double check this, you could double check it. If you take cosine pi plus I times sine pi, this is what Eulers Identity would say. You expand this, double checking like earlier. Cosine pi, that's -1 plus I sine of pi, that's I times 0. So this part gives me 0 is -1. I told you. Did I not tell you? So that was just to check. So -1 e is equal to I times pi. That means if I add 1 to both sides, I get that 0 is equal to e to the I pi plus 1. Now this, my friends, this is timeless. Timeless. One of the timeless identities of all times. With all the big players here. All the celebrity numbers here. This was a celebrity party. This is like if there was an A-list party in Hollywood, like the Oscars night, and all the famous people are there. If there was one for numbers, this would be it. All the famous numbers are here. Count them. How many famous numbers? 0, the additive identity. Check. 1, the multiplicative identity. Check. E, the most elegant number in the world. Check. I, the most mysterious imaginary number in the world. Check. Pi, the one that gets more credit, but it's not that good. Well, it's alright. Check. All the famous players are here, right here. And one of the most famous and celebrated equations of all times. People put it on their backs, they tattoo it, they put it on plants. This is big time. Okay? So, now let's go, let me think. So for today, I think we should give this a rest here. Just take a look at the big picture. There's a lot of things to do here. You know, we got to understand E, what we mean, how to prove it, why, and all that stuff. But for now, we just want to take on a modest goal. Practice crossing this bridge, which is really easy. If you were good at converting in polar coordinates, just practice that for the homework. Any old binomial or standard form complex number, you should be able to convert using the same r and theta that we had before. Even if they're monomials, doesn't matter. Binomials, doesn't matter. You should be able to convert both of these. Sometimes they have an r here. If the r is not 1, well, they always have an r, but sometimes the r is equal to 1. So you don't see it. Generally, they look like this. R, E, I, theta. Practice this bridge here, and then tomorrow or the next time we meet, we will expand on that and do some amazing things like take the square root of I. If you ever wonder what's the square root of I, I challenge you, find a number that when you square it, you get I. It's not that easy in this world. This is the world of Mondays and Prozac and all that. It's not that easy to do that, but here, we're going to cross this bridge here, come into this world, and everything will be easy, a piece of cake. Okay? So for now, just practice crossing the bridge. I'll stop here, and you guys can do the homework, and we'll see us here next time. Okay? Peace. Peace.